coupling spatial and temporal coding in retina and V1. Now the input signal S depends on space X and time t. The correlation between two spatial temporal signals is assumed as translation invariant in space and time. So it depends only on the spatial displacement x1 minus x2 and the temporal difference t1 minus t2. We have learned for signals with translation invariant correlations, the principal components are non-Fourier waves. Now the wave is in both space and time with frequency k, spatial frequency k, and temporal frequency omega. This means that following our efficient coding scheme, the first step for the principal component decomposition, in this step, the original signal is transformed by this Fourier transformation matrix with these elements. The matrix K0 is the product between a Fourier transform in space, K0 superscript x, and a Fourier transform in time, K0 superscript t, with these respective elements. In the second step, gain control, we know that the gain is determined by the signal to noise in each Fourier component. And since this signal power decreases with both the spatial frequency k and temporal frequency omega, this gain function should be unimodal in both the spatial and temporal frequencies. As illustrated in these data from example neurons in LGN. So here, this is the spatial frequency, and for each of these curves, the gains are peaked for intermediate spatial frequencies k, and this is so for each curve, one for frequency 0.65 in red, and another for 10.4 Hz in black, and another for 20.8 Hz in blue. And if we compare these three curves, you can see that the gain is highest for the intermediate temporal frequency 10 Hz. For the third step, multiplexing transform matrix U in both space and time. In space, we can do the inverse Fourier transform like we did for the efficient spatial coding when we focused on the spatial dimension alone. And in time, we can do the inverse Fourier transform in time like we did for the efficient temporal coding, focusing on time alone. This is for making small and translation invariant resistive fields, and this is for making temporal resistive fields that are causal and have a minimal temporal spread. We note that this is done by having this phase function phi, and here we need a phase function of temporal frequency omega for each spatial frequency k. Combining these three stages together, we will have this spatial temporal filter as the efficient coding filter, coupling space and time. You can see that generally it is a filter with this sensitivity gain function, bandpass filter, G as a function of k and omega. And of course, to make this filter real, these phases need to satisfy these constraints. Let's look at this more closely. This can be written as here, okay, over here. Now the factor k is taken out, so therefore here omega from here is becoming omega over k. And now we can write this out again in this form, replacing omega over k by minus v. And now we recognize that this v is the velocity for this spatial temporal wave, and this spatial temporal wave has spatial frequency k and temporal frequency omega. Okay. Of course, we have many different frequencies k and omega. So in this frequency space, there is a motion velocity v associated with each pair of k and omega. And these pairs on this line, they share the same velocity v. And frequencies on this line have the opposite velocity. Therefore, if the corresponding sensitivities here, gk omega, for these corresponding frequency pairs are equal, which can be assumed if the natural scene has equal signal power in these corresponding frequencies. Note that the gain is only determined by the signal to noise in these frequencies, so therefore if they have the same signal power, then they should have the same signal gain according to the efficient coding assignments. Then if we integrate over all these frequencies, and different velocity directions for a single filter will cancel each other, so the whole spatial temporal filter is not preferring any motion direction over another, and this filter is therefore not tuned to any motion direction. And this is the case for retinal ganglion cells in cats and monkeys.